were developed by teams from across the nation, from high schools and universities to NASA field centers. Da Vinci was developed by a student-led team at North Idaho STEM Charter Academy. It's designed to connect to students around the world by broadcasting education-related messages through amateur radio in Morse code. It also carries a Globalstar modem and ArduCam, allowing users to upload digital messages or see photos of Earth from orbit.
I don't know if anyone remembers like the Ovaltine messages and stuff on the radio way back when, but our goal is to do something like that where they have to tune in every week or every other week to get this new message and decode it and really dive into that information so that they develop an interest in space and they say, oh, hey, I can communicate with something that's not even on this planet.
RSAT was developed by a team of midshipmen from the U.S. Naval Academy in Annapolis, Maryland. This crab-like CubeSat has a pair of robotic arms designed to grab a host satellite and maneuver around it to take photos, or potentially even make repairs if a spacecraft isn't working properly. The CubeSat STF-1, or Simulation to Flight 1, is a collaboration between NASA Independent Verification and Validation Program with West Virginia University and small businesses. STF-1 will monitor space weather over Earth's poles and test the durability of new materials for use in LEDs. But it's also designed to demonstrate a simulation and test platform to aid in the development of future CubeSat missions. These CubeSats show that small satellites have an important and growing role in space exploration. NASA's Venture Class Launch Service was created in 2015 to provide CubeSats their own ride to space, expanding launch and science opportunities for small satellites and sparking a brand new segment of the space launch industry. Rocket Lab's Electron rocket is one of two vehicles NASA selected for Venture Class missions. It's smaller and lighter than other launchers in NASA's stable, but that's the whole point.
The intent is for the Venture Class launches to occur at a rapid pace that match the iteration and design cycle that CubeSats can go through. So instead of having a launch for a primary mission once every 2 years, once every 5 years, the real goal is to see Venture Class rockets get to a cadence where they can see regular access to orbit.
Many of the CubeSats on the Alana 19 mission are designed to benefit future missions. Shields 1 was developed by NASA's Langley Research Center in Hampton, Virginia. Its objective? To test materials that could be used to shield spacecraft against radiation.
This is a radiation effects experiment where we're looking at the performance of the materials and the electronics, and it would have a potentially large impact for improving performance of future spacecraft.
NMTSat was built by approximately 50 undergraduate and graduate students, primarily from New Mexico Tech in Albuquerque, New Mexico. It's designed to use onboard sensors to collect data on Earth's magnetic field, take atmospheric weather measurements, and carry out an optical beacon experiment. The next spacecraft was developed by teams on opposite sides of the country in Florida and California. It's called CHOMPT, which stands for CubeSat Handling of Multi-System Precision Time Transfer. This mission is a collaboration between the University of Florida in Gainesville and NASA's Ames Research Center in Mountain View, California. CHOMPT uses lasers instead of radio waves to demonstrate new ways to navigate and network satellites in deep space. The Advanced Electrical Bus, or ALBUS, was developed by NASA's Glenn Research Center in Cleveland, Ohio. ALBUS will demonstrate shape memory alloy mechanisms for deployable solar arrays. It'll also serve as a pathfinder for high power density CubeSats.
The shape memory alloys themselves are really good technology because they are low mass, they can produce low shock, and we can reset them. So we can actually reset our mechanisms to test it again to deploy it to make sure we're going to have a successful mission.
While the CubeSats are prepared for flight, their ride, the Electron rocket, begins to take shape. Fully assembled, the Electron stands nearly 56 feet tall, a smaller rocket dedicated to launching small payloads. It's a 3-stage carbon composite vehicle topped by a payload fairing to protect the CubeSats during launch. The Electron's engines and avionics are manufactured here in the United States at Rocket Lab's facility in Huntington Beach, California. In fact, the company's Rutherford engine is the first ever oxygen kerosene rocket engine built using 3D printed main components. Then they're sent to Rocket Lab's facility in Auckland, New Zealand. Here, the company puts its engines to the test before final integration. It's also where Rocket Lab manufactures the vehicle's stages and payload fairing. But until the rocket is assembled and tested in New Zealand, the CubeSats will wait in California. It will all come together when the spacecraft arrive from Huntington Beach just a few weeks before launch. CubeSail was built by the University of Illinois at Urbana-Champaign in CU Aerospace. It carries a 250-meter solar sail ribbon, technology that's being evaluated for use on future spacecraft, such as scientific missions to interstellar space.
And CubeSail is going to be doing a technology demonstration of the deployment technique as a stepping stone towards even larger missions we have planned on the road, like iSail and UltraSail.
The ISX CubeSat, or Ionospheric Scintillation Explorer, is a collaboration between SRI International and PolySat at Cal Poly San Luis Obispo, California. ISX is designed to take a closer look at plasma fluctuations in the upper atmosphere and learn more about how they affect radio communications with satellite. Up next is Ceres, the CubeSat Compact Radiation Belt Explorer. It was developed by NASA's Goddard Space Flight Center in Greenbelt, Maryland. Ceres will fly into Earth's Van Allen radiation belts to study the high-energy particles streaming toward the Earth from the Sun and learn more about how electrons in the radiation belts are energized and lost.
CubeSats go into the clean room and they do their standalone processing. So that's any sort of checkouts, charging. Basically, they're getting ready to get into that final package, the dispenser. That's the piece of hardware that's actually going to launch them out into space off of the rocket.
November 2018. With the Electron rocket ready for final integration and launch, the CubeSats are shipped from California all the way to Auckland, New Zealand. But the Electron rocket elements and all the Elana 19 CubeSats still have to make one more journey on Earth. It takes a caravan of trucks about 8 hours to make the 575-kilometer journey from Auckland to Rocket Lab's Launch Complex 1 at Mahia Peninsula on the island's east coast. But this remote launch site is worth the drive.
So from one single launch site, we can launch all the way to 39 degrees inclination, that's due east, all the way up to sun synchronous, which is about 98 degrees depending on the altitude. So that's the widest range of inclinations available from any launch site in the world.
On the ground at the Mahia Launch Complex, the rocket stages are carefully brought together and inspected to ensure everything is perfect. The CubeSats are installed on the Electron payload plate, the interface between the rocket and the satellites. Then Elana 19 is encapsulated inside the Electron rocket's payload fairing, where the CubeSats will stay until they're in space. The entire rocket is manually rolled out to the launch pad for a rehearsal of the launch day that's quickly approaching. Liftoff is planned for December 12, 2018, and the vehicle is ready. But dangerously strong winds keep the Electron on the ground for 4 more days. Their fortunes change on December 16th, when the winds aloft finally go green.
5, 4, 3, 2.
The Electron rocket's 9 Rutherford engines ignite. History is made. Less than an hour into the flight, the Elana 19 CubeSats are released. Instead of hitching a ride, these small spacecraft have a dedicated ride that can deploy each one to just the right orbit for maximum science. Elana gives students and teachers a low-cost pathway to space to test new technologies, make new discoveries, and create new connections to each other and the future. Small satellites, big dreams, and even bigger potential for future CubeSats needing a Venture-class ride into space. To launch with Elana, visit nasa.gov/Elana.
Hello, welcome to NASA Science Live, your chance to go behind the scenes at your space agency and get your questions answered by NASA scientists and experts. I'm your host, Gray Hautaloma, and today we're here at the American Geophysical Union Conference in San Francisco. It's one of the largest conferences in the world, and people are presenting papers on all kinds of topics. We're going to learn more about our OSIRIS-REx mission, NASA's first mission to get a sample from an asteroid and return it to Earth. We want you to ask your questions to our NASA experts by using the hashtag AskNASA at Twitter and on Facebook or in the comment box wherever you're watching this. I'm going to head to the NASA booth right now to meet those experts, so please join us there, but first watch this video about OSIRIS-REx.
On September 8th, 2016, in Cape Canaveral, Florida, OSIRIS-REx began its journey, NASA's most ambitious sample collection attempt since the Apollo program. After 2 years, including a gravity assist from Earth, the spacecraft arrived at its destination, asteroid Bennu. As OSIRIS-REx drew near, Bennu grew in detail from a few tiny pixels to a surprisingly rugged world, littered with giant boulders. The spacecraft has used its instrumentation to map the asteroid from all sides, mapping it in unprecedented detail. The mission team has been analyzing the data, scouring Bennu's surface to select the best sample site. Now, with just months to go before sample collection, the team has narrowed its target down to 4 potential sites.
Hello, and thank you for joining us in the booth here at AGU, the American Geophysical Union, for this special edition of NASA Science Live. Today, we have a big announcement from the OSIRIS-REx mission. OSIRIS-REx is NASA's first mission to retrieve a sample of an asteroid and return it to Earth. The mineral particles that make up Bennu, the asteroid that is being orbited by OSIRIS-REx, they could be as old as the solar system itself. Dying particles from stars could have formed the planets and our own sun. And now we're going to get a sample from that asteroid and return it to Earth. And we're going to find out from where today. We're going to get maybe upwards of 30 sugar packet samples worth. So it's very exciting, and I'm really pleased to have here today some mission team members. So please let me welcome Danny Delagostino.
Hey, Gray.
And Mike Moreau, and they're going to tell us a little bit more about the mission and the challenges and where we go next. So I guess the big obvious question is why? Why did we want to study Bennu?
Yeah, that's a great question, Gray, and I'm really excited to talk about Bennu and the mission ahead of this announcement. So Bennu is a near-Earth asteroid, and that means its orbit is in close proximity to our own planet, and it was fairly accessible for us to send a spacecraft there, so that's one reason. But because of its close proximity to planet Earth, it's also a potentially hazardous object, and so by sending a spacecraft there and flying in formation with Bennu for over 2 years, we're going to get a much better sense of Bennu's orbit and be able to better predict whether or not it is a hazard in the coming decades and centuries. But finally, Bennu is composed of water-bearing minerals, and that was a discovery we made very early on in the mission. And there's early indications that it might have organics as well, so we think that Bennu looks a lot like the objects that might have delivered the precursors to life to early Earth. And so it's also exceptionally scientifically exciting to be in orbit around this surface.
Wow. I can't wait to find out more about it. I know it gave us a lot of surprises. Do you want to tell us a little bit more about that, Mike?
Yeah, so one of the biggest surprises when we saw what Bennu looked like is what's on the screen here. It is just covered with rocks. So on the table next to Danny is a model of Bennu. Evaluate the whole process and the data set that we would use for site selection and make some
Spectral interpretation, resource identification, regolith explorer. So there's a
Wow.
lot there.
That's pretty good. Okay, well, I hope that answers that question. Let's see what we got. Another one. Gemfef on YouTube asks, what are you looking for when you go to the sample site? When you're searching the sample site, what are you looking for?
Yeah, so the primary thing that we are looking for is the presence of sampleable material. We're also very interested in whether or not the site is safe. But from my perspective as a scientist, I'm very interested in whether or not these sites might have organic material or things that we think are similar to the precursors to life that were eventually delivered to Earth. Is there anything you want to add about the safety?
From my perspective, our number one goal is to keep the spacecraft safe while navigating down to these potential tag sites. And so we're interested in the fact that some of the sites have very large boulders in the vicinity of them and smaller rocks within the area we're trying to contact that could be potentially hazardous to the spacecraft. So we've had to take precautions in order to keep the spacecraft safe.
Okay, well, I want to thank you both. That's been really fascinating. And now we've got a video that we're going to show you some of the surprises at Bennu that they were talking about. That's going to go into greater detail about it. So let's watch that right now.
In late 2018, as NASA's OSIRIS-REx spacecraft neared its target, Bennu, the asteroid grew in detail from a few tiny pixels to an incredibly high-resolution image. OSIRIS-REx confirmed the asteroid's basic shape, which was originally observed in 1999 by ground-based radar at Arecibo Observatory. What scientists didn't expect was just how rough and boulder-filled the asteroid would turn out to be. While it can be difficult to fully grasp Bennu's unfamiliar surface, it's helpful to understand the scale of what you're seeing here. In this image, the brightest boulder is the length of a horse, and the large boulder in this image is the width of a soccer field. Another challenge for the mission is the asteroid's small size and weak gravity. This means that OSIRIS-REx needs to fly daringly close to the surface in order to enter into orbit. With its orbital A phase, OSIRIS-REx successfully entered the closest ever orbit for a spacecraft, setting a Guinness World Record in the process. Then, 6 months later, it beat its own record during its orbital B phase and approached to within a few hundred meters of the rocky surface. Because OSIRIS-REx flew so closely over the surface during orbital B, the team was able to map the topography and shape of Bennu better than we have our own moon. In addition to mapping asteroid Bennu, OSIRIS-REx plans to collect and return a sample back to Earth. To do that, the spacecraft will carefully tag the surface of Bennu. The OSIRIS-REx team has selected 4 possible sample sites for the mission: Osprey, Kingfisher, Nightingale, and Sandpiper. The spacecraft has been closely imaging these sites from different angles to select the best touchdown spot for OSIRIS-REx. What was originally envisioned as a smooth and easy touchdown on Bennu's surface has become a complex endeavor to tag a small, crowded space on the asteroid, an area no larger than a few parking spots, by mid-2020. The OSIRIS-REx team has already pushed the boundaries of scientific exploration, going from ground-based radar images all the way to being a few hundred meters from the asteroid's surface, and is now mere months away from a sample collection attempt.
All right, well, that video gave us a lot of perspective on just how hard it has been to explore Bennu once the spacecraft got there and all the surprises that the team encountered. But we are now getting ready to select that sample site and tell the world about it. And we've heard a little bit about Bennu and where it is, what it looks like, and now we're going to get a little bit more into the why of why we do this. I'm pleased to be joined by Dr. Lori Glaze, who's head of the Planetary Science Division at NASA headquarters.
Hi, Gray.
Welcome, Lori. So, tell us, why do we do sample return?
It's a great question. So we've been observing Bennu now for about 20 years, first observed using ground-based telescopes, and then over that 20-year period we've continued to observe the asteroid using ground-based and space-based observations, and then over the last year, of course, we've been able to observe using the OSIRIS-REx spacecraft, but all of those measurements and observations are remote sensing observations. They're done from a distance, and there really is just no substitute for being able to actually pick up some of that material from the surface and bring it back to Earth. By bringing it back, that allows us to use the full capabilities of all of our state-of-the-art technologies and laboratory facilities to analyze those samples, to answer some of the really big questions that we have that Danny was talking about when she was sitting here. And not only can we answer those questions using our facilities today, but we'll actually preserve most of the sample for all of the generations to come, that they can then use new facilities and new instrumentation that we haven't even dreamed of yet.
Wow, that's going to be amazing. So what in particular do we think we'll learn from Bennu?
So Bennu is actually going to address several major questions, and three big ones in particular. First off, you heard, or you said earlier, that Bennu we think is a really old object that's really a remnant and preserved from the very earliest parts of our solar system. So by looking at those samples, we'll get insights and information telling us about what conditions were like when the solar system formed. And then Danny talked about how we think there are hydrated minerals and perhaps organic molecules on the surface. And by looking at those, we'll better understand how those types of materials were delivered to Earth and perhaps were the seeds for how life actually began to form on Earth back in the earliest times. And then finally, it's also going to help us better understand what types of resources might be available on these asteroids that are out there, that as we start to take human exploration beyond the moon and start to go other places, there may be resources there that may be of use to us in the future.
Well, these are some really big questions. And I know OSIRIS-REx is a unique mission, but there are other missions in place going forward to get samples from other places, building on the Apollo moon rocks we have and going to Mars and so forth. How does that whole field fill in this?
Absolutely. So, of course, the Apollo missions were the first missions to actually bring samples back. We get natural samples all the time, of course, with meteorites that come through the atmosphere. But the Apollo missions brought those samples back. We're still analyzing those samples today, 50 years later. We just opened up some pristine samples a few months ago, or just trying to look at those with our new technologies, as I was saying. But we also are working right now with the Japanese Space Agency on their mission to visit another asteroid called Ryugu, and next December they'll be returning some samples from Ryugu that we'll be able to study another asteroid in comparison with Bennu. And then Japanese Space Agency is also planning a mission to the Mars moon named Phobos to bring back samples from there. And of course, NASA, next summer, will be launching the Mars 2020 rover, which will land in Jezero Crater, drive around, and collect samples from Mars that will be left on the surface for eventual return by a Mars sample return mission.
Well, there's a lot going on in this area. Thank you so much, Lori, for that perspective. Really appreciate it.
My pleasure.
Well, now we're going to bring up the man with the answers. Dante Loretta is the principal investigator of OSIRIS-REx, and his team has been working round the clock since OSIRIS-REx arrived at Bennu last January 1st, and they discovered all those surprises we've been talking about. And he's going to give us an overview of how they narrowed down the multiple candidates for site selection and then announce the real one. So Dante, tell us about the whole process of narrowing these down.
Yeah, thanks, Gray. As you can see from the map of the asteroid behind us, when we first got there, the most obvious feature that we saw were these abundant, very large boulders, and overall a rough and rugged surface, very different than what we designed the spacecraft to sample. We were looking at sampling areas that were 25 meters in radius across, and quite honestly, I thought it was going to be obvious from the first images where the sample regions were and that it was going to be a straightforward site selection, and it was nothing of the sort. So the first thing to do was to complete the global characterization of the asteroid. We used our camera systems, we have laser altimeters for getting the topography, and we have several spectrometers for analyzing the mineralogy and the chemistry. And the science team did an amazing job of synthesizing all of that information and making a whole series of maps of the asteroid's surface. And then we went through several different ways to characterize it. We had the team looking at the imagery and the other data to pick areas that looked sampleable. We used machine learning algorithms. We also wrote specific software to find flat areas on the asteroid surface. And we also crowdsourced some of this information out to get the community involved in helping us select the sites. After that process, we actually had 50 different areas on the asteroid surface that looked like they might be interesting for us. And so I set it up kind of a tournament-style bracket. We ultimately got down to our Sweet 16 and then the Elite 8 and to the Final Four, where we are right now, about to crown the champion and the runner-up of this process.
All right. Well, I understand you have some really cool videos of those Final Four sites. So why don't you go over them with us?
Yeah, let's take a look at the Final Four candidate sample sites. So we're going to start out with the Osprey crater. This is about 20 meters in diameter. One of the key features is the big flat rock that's 5 meters long. We call that 12 o'clock rock because it's almost pointing due north, and it kind of sets our orientation for us. It does look like it has some fine-grained sampled material, especially right towards the central region and in the trough or the ridge, beyond the ridge to the east there. But it is a kind of a rough and rugged surface, and so we do worry that it might be a little more challenging to ingest those 2 centimeter sized particles from its interior. But overall, the surrounding area, because it's up on kind of a hill, it's relatively free of hazards that we might fly into on the back away from collection. Let's take a look at the next one. This is the Kingfisher site. So this is similar to Osprey in that it's in an equatorial region, and we like the equator because the navigation team has higher accuracy when we're targeting equatorial sites. This is a smaller crater, about 10 meters in diameter. One of the most intriguing features are the 2 smaller craters that we in fact call the Mickey Mouse ears. Those look like the best, finest grained sampleable regions on the asteroid, but they're really small, on the order of 2 meters across, and we know we can't get the spacecraft into a spot that tight, but the hope was that that same kind of fine-grained material was accumulating in the center of this smaller crater. If we take a look at our next candidate, this is the Nightingale crater. So unlike Osprey and Kingfisher, this one's at high latitude up in the northern region of the asteroid. It's a crater about 20 meters in diameter. It's characterized by a lot of apparently fine-grained material. We do see a few large boulders that look like they've rolled down into the lowest depression over here on the right side of our image. And the most characteristic feature for me is this large wall of tall rocks. That does represent a potential hazard to the spacecraft, because when we make contact with the surface, the only thing that touches it is the sample collection head at the end of a long robotic arm. That may tip over a little bit, and we back away at whatever angle we've tipped to, and we're concerned that we might fly into some of those hazards. So let's take a look at the final site. This is the Sandpiper site. So this is also a high latitude site, except it's in the southern hemisphere of the asteroid. And unlike the other 3 sites, it's part of a much larger crater, about 50 meters in diameter. And what's really interesting here is the site itself is on one of the slopes of the crater wall. And it looks like there's a whole series of boulders that are kind of rolling down this terrain like a slow motion landslide. But the Sandpiper site appears to be shielded from that process by this large rock off to the south. So there's a whole swath of the crater wall that's relatively free of boulders and appears to be dominated by that fine-grained sampleable material.
All right. Well, those all look like great candidates. Well, you've seen them all now, and some of those space rocks you're seeing right now are going to be brought back to Earth. That's pretty exciting. So, Dante, do you want to tell us which one you've picked?
I will. So I'll say that just thinking that we're going to get this sample back to Earth sends chills down my spine. So the winner of the OSIRIS-REx Site Selection Championship is the Nightingale site.
All right. Make some noise, audience.
Thank you. So we recognize that this does have some hazards around it, and so we are doing a lot of work to make sure that we're targeting the safe regions, but this one really came out on top because of the scientific value. The high latitudes means that it stays relatively cool, and the primary objective of OSIRIS-REx is to bring back organic material and water-bearing material from the early solar system, and being in those high latitudes we think gives us the best chance to preserve that kind of material. Since we are dealing with a site with some hazards nearby, we have put some safety mechanisms onto the spacecraft. The spacecraft can actually tell if it's coming down onto a hazardous region and wave off and abort and fly away, fire thrusters and fly away from the asteroid. That may disturb the surface and make that region unsampleable. So we also have a backup site. The runner-up is the Osprey site. That's the 20-meter crater near the equator. We know we can get in there. It doesn't have the hazards that Nightingale does, but it also may be more challenging to collect a sample, but we think the lower hazards makes it the right choice for the backup.
Well, thanks for that, Dante. We do have a bunch of questions flowing in from social media. Again, use the hashtag AskNASA if you have one. And let's just go right to someone from in our audience. Aaron in the audience asks, what is the biggest challenge of the site?
So the biggest challenge of the Nightingale site is those large boulders that are off on the eastern edge of the crater, because that tallest one, I colloquially call it Mount Doom because it has the classic kind of peak shape that we're familiar with from the literature. That's about 7 meters tall, and then when you're down at the bottom of the crater, that's another 3 meters. So we're talking 10 meters or 30 feet. So it's a substantial building-sized obstruction, and we're trying to get into a crater that's on the order of a few parking lot spaces wide. So we are doing a really tight job parking that, and we're aware that we have hazards around us. So precision navigation to that sampled material is our biggest challenge.
Wow, well that's going to be some amazing engineering. Well, that's all the time we have for questions right now with Dante, but keep sending them in, and thank you so much, Dante, and congratulations.
Thank you.
So right now I'm going to invite Mike Moreau back to the stage, and he's going to talk a little bit more about the engineering that makes this amazing sample return possible. We have an instrument aboard OSIRIS-REx called the TAG-SAM, which is actually going to ingest the sample in a very unique way that Mike's going to explain, and then cache that sample and to return it to Earth later after we get it. So welcome back, Mike. So tell us a little bit about the challenges of the sample collection using this instrument.
Yeah, so you can imagine when the OSIRIS-REx mission was being formulated, engineers had a really interesting design challenge, and that's how do you collect a sample from an asteroid millions of miles away using a robotic spacecraft? And the TAG-SAM is the innovation that our partners at Lockheed Martin came up with to do just that. The TAG-SAM, as is shown here in full scale, and it actually sits at the end of a robotic arm at the end of the spacecraft. So the TAG-SAM is the only piece of the spacecraft that will touch the surface, and in doing so, once contact with the surface is detected, there will be a nitrogen gas bottle that is fired, which stirs up the surface underneath the TAG-SAM, churns up some of that fine-grained material, which will then be captured in the outer ring here. Once the spacecraft has been in contact for just a few seconds, it will fire its thrusters and back away, hopefully with the sample in hand.
So there's so many contingencies potentially here. What happens if it gets too close and it realizes it's a hazard or there isn't enough to even sample?
Yeah, so Dante alluded to this in his remarks. We've had to make some changes to the capabilities of the spacecraft to allow us to navigate into a site like Nightingale. And we've implemented something called a hazard map, which will be uploaded to the spacecraft. And then the onboard knowledge that the spacecraft has of where it's coming down, if it detects we're coming down on one of these hazards or too close, it will back away and we'll have a chance to try again.
Wow. Well, that's a good backup. What happens once you do get the sample collected? What happens to it?
So once we back away, the next couple of days will be spent assessing the health and safety of the spacecraft after contacting the surface and trying to figure out if we have a sample. The two primary ways that we'll figure out if we have a sample, one is just simply imaging the TAG-SAM with the cameras on board the spacecraft. We'll be able to see if there's material that's captured inside the ring. The other technique that we're going to use is called the sample mass measurement. And we will be actually spinning the spacecraft in a little pirouette, and it will help us determine the mass of sample that's at the end of the arm.
Wow. So you're an engineer. We have a question from Andrew Siegel on YouTube, wants to know, how do you decide the maneuvers the spacecraft has to do, and how do you assess your options in such a tight space?
That's a great question. The navigation team and our Lockheed Martin team are spending many hours designing the trajectories that have allowed us to fly in proximity to Bennu and collect all of the images that are shown in this mosaic on the screen. And they're right now that we've selected the Nightingale site, doing the final designs of the trajectory that will take us from orbit down to the surface and contact the sample. And there's been a lot of work already done to determine those trajectories and how accurately we can actually contact the surface.
At Benjamin on Twitter wants to know, how is the team's work changing now that you've got the focus? You know where you're going.
The team is incredibly excited now to have the site selection decision, and Nightingale is an exciting site to go into because of the challenges it's posing. And the team has really risen to the challenge, both to come up with how we would make the decision about the best site, but also to convince ourselves that we can actually get there and navigate the spacecraft successfully. So the team, I think, is really excited to be able to move forward and put all of our attention towards tagging at the Nightingale site.
Great. We've got just a couple more real quick here. Maybe, I'm not sure if you'll be able to answer this yourself, but Lucy on Periscope wants to know, are there going to be precautions for quarantine once this is brought back?
That's not my expertise, but there will be great care taken when the sample returns to the Earth. It will enter the atmosphere in a small sample return capsule that will land in the Utah desert, and there will be a huge effort to recover the capsule and then transport it to Johnson Space Center, where there are facilities in place to curate and make the sample available to the public for analysis, for scientific analysis.
Thanks so much, Mike, and I want to thank everybody who was on the show today. That's all the time we have right now, but please continue to go to nasa.gov/OSIRIS-REx and keep following the mission. It's only going to get more exciting as it gets closer and does these sample return maneuvers and then gets the sample back to Earth later. So that's all the time we have for now. Until next time, let's go play tag.
Hey, you're watching NASA TV, on the air and online every day, on this planet and beyond.
setting a bold goal in human space exploration with the Artemis program,
to return American astronauts to the moon within the next 5 years.
while celebrating Apollo's historic first steps onto the moon, and kicking off the 20th year of humans continuously living and working in space. Here's a look back at those things and plenty more awesomeness that happened this year at NASA. Our plan to return humans to the moon with the Artemis program was adjusted, with 2024 now being the new target for landing the first woman and next man on the lunar surface.
This is a critical capability for not just a sustainable lunar return, but also an eventual journey to Mars.
Our Commercial Lunar Payload Services, or CLPS initiative, selected commercial moon landers to deliver science and technology demonstrations to the surface in 2021 that could pave the way for the arrival of astronauts. One tech demonstration, known as Viper, is a lunar mobile robot that will collect data on water ice to inform the first global water resource maps of the moon. We also talked to American companies about developing reusable lunar landers and systems for future human missions to the moon. And we selected a company to provide power and propulsion for our Gateway, an outpost to orbit around the moon from which astronauts will shuttle to and from the lunar surface. And when we do go, our Orion spacecraft, its European Space Agency-built service module, and our RS-25 engines and Space Launch System rocket will get us there. We made significant progress in 2019 building and testing these systems for our upcoming Artemis I uncrewed flight test. And what's a next-generation mission without next-generation spacesuits? Took care of that too in 2019 with new spacesuits that fit better and provide better mobility for astronauts exploring the lunar surface. And from our Mars robotic explorers, for the first time ever, our InSight lander measured and recorded a likely Marsquake. Our Mars helicopter technology was put through some rigorous testing in preparation for its launch on the Mars 2020 rover mission. Also taking that ride will be more than 10 million names of Earthlings etched on dime-sized microchips installed on the rover. It was a milestone year for humans in space. We began our 20th consecutive year with humans aboard the International Space Station and conducted several important spacewalks, including the first ever by an all-woman team of spacewalkers, a series of complex spacewalks to repair a cosmic ray detector, and an outing to help install a new docking adapter to accommodate future arrivals of various spacecraft, including commercial crew spacecraft built by Boeing and SpaceX.
Ignition, liftoff.
The SpaceX Crew Dragon spacecraft made the first ever docking to the International Space Station during its uncrewed flight test for NASA's Commercial Crew program. Meanwhile, NASA and Boeing are learning lessons from the uncrewed test flight of Boeing's CST-100 Starliner, which launched on December 20th, but was unable to dock with the space station. 5 successful commercial cargo missions with Northrop Grumman and SpaceX delivered more than 32,000 pounds of science investigations, spacewalking tools, and critical supplies to the station. A new policy was announced in 2019 making the space station available for commercial business ventures. And results from our landmark twins study of astronaut brothers Mark and Scott Kelly were published. Data from the study could help maintain crew health during exploration missions to the moon and Mars. Lots of happenings in our solar system and beyond. Our New Horizons spacecraft rang in the new year with a record-breaking flyby of a Kuiper Belt object 4 billion miles from our sun. We announced a new mission to Saturn's icy moon Titan to search for the building blocks of life. Our Sophia Airborne Observatory detected helium hydride, the first type of molecule to ever form in the universe, in a planetary nebula some 3,000 light-years away from us. We helped capture the first ever image of a black hole and its shadow. Data from our Hubble Space Telescope showed water vapor for the first time in the atmosphere of a planet outside our solar system that resides in the habitable zone. Researchers hope to further study 3 new worlds discovered by our TESS spacecraft 73 light-years from Earth, a nearly Earth-sized one next to 2 others known as mini-Neptunes. The first data shared from super-close, record-breaking flybys of our sun by NASA's Parker Solar Probe revealed new insights into solar dynamics that can affect astronauts and technology in space.
Pegasus away.
And we air-launched a mission to help us better understand the physical processes at play in the ionosphere that are potentially detrimental to radio communications, satellites, and the physical health of astronauts. Highlights from the world of space technology include the launch of several NASA technology demonstrations aboard a SpaceX Falcon Heavy rocket. The demonstrations are designed to test less toxic fuel for spacecraft, new ways to navigate in space, processes affecting space communications, and to look at the space environment around Earth and how it affects us. 3 free-flying robots sent to the space station on Northrop Grumman's Cygnus spacecraft will help develop and test technologies for use in zero gravity and do routine chores so astronauts can do other important tasks. Our 3D printed habitat channel
you hear me?
Second Baptist School and distinguished guests, the International Space Station has you loud and clear.
Hi, Christina. My name is Don Davis. I'm the head of school at Second Baptist. I have Senator Cruz here with me this morning, and he's going to ask you the first question. Christina.
Good morning, sir. My pleasure to be with you.
Good morning. Thank you for the incredible job you're doing. I got to tell you, you've got about 1,100 kids amazed to be watching you floating in front of their eyes up in space over Texas. We're proud of you, and we may have a few junior astronauts who are going to come join you on a later mission. So let me ask the first question. How is training